Welcome to the first part of a series of lectures on climate change, peak oil and sustainable development. In this first lecture, I'd like to focus on the subject of climate change. Is it actually happening? If so, what's causing it and who might be the culprits? In looking at these questions, I think you have basically three options. You can either believe the scientists, the large majority of whom believe in climate change, or you can believe the climate skeptics and the radio talkback hosts, some of whom debunk the whole concept, or at least question whether in fact humans are responsible if there is any global warming happening. And the third thing you can do is really look at the data yourself and try to make up your own mind. Let's start with the scientists. You'll often hear said on conversations that the majority of scientists believe in the theory of global warming and that humans are basically responsible for it. But where's the evidence for that? Well, the study above examined something like 11,900 abstracts from peer-reviewed articles in climate journals in the scientific literature, which is a pretty large sample. And it concluded that a vanishingly small percentage of less than 3% of those papers questioned or contradicted, if you like, the overall consensus that global warming is happening and that humans are responsible for it. Of course, scientists can be wrong. New theories coming out are often initially debunked, such for example the plate theory of continental movements or Einstein's relativity theory. There's still a lot of active debate, for example, about Darwin's theory of evolution, where there is increasing evidence of what's called epigenetics and its role in modifying the simple theory that modification of DNA is the only path to evolutionary change. There's still a lot of debate amongst physicists about the origins of the universe, the role of dark matter and dark energy, for example. We understand very little about that, or exactly how gravity works. So scientists actually live with the idea of uncertainty, and indeed the whole concept of a scientific hypothesis is simply that it is the best explanation of the data, and it can always be revised if new information becomes available. The key to scientific thinking is that we are trying to explain observed behaviour, or what we can observe from what's going on around us in the world and in the universe. And hence data is important to scientists. Indeed, it's absolutely crucial. What about the radio talkback and climate skeptics? Well, given the variability of data on climate and the complexity of the climate system, and we'll talk more about that later in this lecture, it is in fact quite surprising that there exists such a level of agreement amongst the scientific community about global warming and its causes. And indeed, it's not at all surprising that there are in fact some scientists, just a small number, who disagree with the current consensus. But what's perhaps surprising is the vehemence of the climate skeptics, most of whom are not scientists and have a very poor understanding of what it means to look at data scientifically. To give you an example, Alan Jones, the well-known broadcaster on radio, in fact used to be my English teacher at high school. He was a rugby coach, indeed he coached the Australian rugby team, but he certainly was never a scientist. And yet he has claimed that global warming is a hoax and it's witchcraft. So it's really up to you to decide whether you want to believe the people who've made a career out of studying complex systems like the climate system, or whether you want to believe people who just sound off on radio. The third thing you can do is actually try and look at the data yourself. And there's some pretty dramatic evidence that the Earth is actually warming. For example, the photographs above were taken a century apart of the Okpaluk Glacier in Alaska. And it's pretty obvious that the one on the right a century later shows that the glacier is disappearing fast. If this was an isolated instance, that wouldn't prove anything. But the reality is the large majority of the world's glaciers are in fact melting and at a very rapid rate in geological terms. So what's really surprising here is not so much that there are changes in glaciers, but it's the rate of change and the rate of shrinkage of the glaciers that's truly alarming. Of course, the best way, the most reliable way to measure, in fact, whether there is a change in climate is to look at the surface temperature of the Earth. And the graphs above show the trends over about the last 150 years. And these represent the average surface temperature across the globe, and I'll talk more about that in a minute. The first thing to be noted is that there is a significant variability. If you look at the top graph, significant variability year to year, and lots of periods where in fact temperatures appear to go down over a year or two or even over a whole decade. But the overall trend is unmistakably upwards by around about 0.8 of a degree Celsius over that period. The trend is much clearer and easier to see when you look at decadal averages. In other words, what's the average been across a whole decade? And you can see that in the second graph. And what that does is it washes out the short-term fluctuations, and it becomes much clearer to see the underlying trends. Now, it's very difficult to actually get this sort of data because you have to rely on, whereas currently we have satellite records and we have weather stations right across the globe. If you go back in time before satellites, then we're having to actually compile data that existed from, was collected from ships at sea and from a much more limited range of sites on land. And therefore, these sorts of records actually have to be constructed in quite a complex fashion. But that's exactly what the scientists are able to do, and why it is so clear that the actual trend from the data is a clear trend in global warming. Another way to look at changes in temperature is to compare averages by location at 2 points in time. And the above compares temperatures a century between 1901 and 2012, basically 110 years apart. And in this case, it's pretty clear that the Earth has warmed almost everywhere. You can see all those areas of red moving right up into the purple. That indicates global or increases in those locations, ranging sort of from half a degree upwards. It's also fairly clear that the warming has been fastest near the poles rather than near the equator. But the trouble is that we don't have very good data going back from Antarctica, for example. So that large area in the bottom part of the graph there, the picture of the Earth for Antarctica is shown in white, simply meaning that we don't have records, accurate records going back far enough for that particular part of the globe to be able to give us that level of accuracy. So the data isn't 100% complete, but nevertheless the overall picture is very clear. Now the point here is that scientists are used to dealing with incomplete data and have developed all sorts of ways of dealing with it. But non-scientists tend to get fooled into thinking that you can't make any conclusions at all unless you have 100% clear data. And unfortunately, many people out there don't understand how it is that you can make inferences based on partial information. Of course, it's not just a matter of looking at temperatures. There are lots of other data sources available, and those graphs above show 4 of them. For example, the amount of spring snow cover in the Northern Hemisphere has been declining. Or under B, the decline in the Arctic summer sea ice, and we'll talk more about that. In C, the change in global average upper ocean heat content, which is effectively where the heat is actually winding up. And in D, the global average sea level change. And again, you can see a fairly strong trend there in rising sea levels. So scientists bring together all of these different sources of data about all different aspects of the world's climate system in order to come to the conclusions that they do about global warming. So if you do take the time to look at the data, it's pretty clear that the world is in fact warming over the last century. But why? This is where it gets more complex, and there are many factors that can alter the heat balance of the Earth. Greenhouse gases are, in fact, one, they act as a blanket around the Earth, and if it wasn't for them, the Earth would be frozen at the surface, as it would simply radiate its heat out to space. So the higher the concentration of greenhouse gases, the higher the surface temperatures. But other things such as sunspot activity, volcanic activity, which for example adds CO2 but also ash, changes in the Earth's orbit, ocean currents, and it's important to realise that ocean currents move not only horizontally, if you like, but we're familiar with the currents in the North Atlantic, but they also move vertically and transfer heat from the surface of the ocean to the depths of the ocean. So all of these things can alter the surface temperature of the Earth. So the Earth is this globe spinning around in space with solar radiation coming in and heat going out. And so there are a complex series of heat gains and losses occurring. The net overall gain or loss in any one year is very small in relation to the total flows. As you can see from the illustration above, around about 340 watts per square metre of incoming solar radiation and about 339 watts per square metre being radiated back out to space. Therefore, the net gain is only of the order of 1 watt per square metre. So it's very hard to measure that in relation to the overall flows, and that's why climate science is incredibly complicated and difficult. Lots of factors influence that. For example, the amount of cloud cover. Some clouds effectively act to cool the Earth by radiating radiation back to space, and some lower down clouds act to warm the Earth by preventing the heat that's being radiated from the Earth itself reaching space. So they actually act to trap the heat. So changes in cloud cover are very complex and do affect the amount of heat coming in and heat going out. The cloud cover in turn is influenced by things like moisture and temperature. So the hotter the Earth gets, the hotter the temperatures get, the more water vapour is released from the oceans, etc., and therefore that increases the amount of cloud cover. So you've got a feedback effect happening that as temperatures change, that can affect cloud cover, which can in turn affect temperatures. So the system is incredibly complex and difficult to unravel. And following the impact of any one change is difficult because it causes follow-on effects, changes to other parts of the system. And that's why you need climate models to attempt to get a handle on how the climate might change, for example, in relation to changes in CO2 levels. The above chart highlights some of the factors that cause climate forcings that lead to warming or cooling of the Earth's surface. And as mentioned before, they're measured in watts per square metre of the Earth's surface. This is an average across the globe. So that you can see in the top collection of the greenhouse gases, CO2, but also methane, hydrocarbons, nitrous oxide, etc. You can see that CO2, which is the brown line there, has a net radiative forcing of about 1.5 watts per square metre. But you can see if you go look further down, aerosols and precursors actually have a range of effects which could be positive, could be negative, depending on circumstances. And there are also changes from albedo, for example, that's the change in the amount of ice radiating energy back to space. Also cloud adjustments due to aerosols, etc. So there are a whole series of factors involved, but the total anthropogenic radiative forcing relative to 1950 is in 2011 has been estimated a bit over 2 watts per square metre. If you go back to 1950, it was estimated to be running at about 0.5 watt per square metre. So climate scientists understand all of these different gases in the atmosphere, how all the different energy levels or energy flows occur, and try to estimate how that total effect influences the world's climate. An important thing to remember is that aerosols or dust from burning fossil fuels actually acts as a cooling effect. So this is why cities like Beijing and so forth, which have very high levels of pollution from the nearby coal-fired power generation and steel plants, etc., receive some level of cooling due to the aerosol effect the localized air pollution, if you like, in parts of China. And to some extent, burning fossil fuels produces both local cooling effects as well as global warming effects. And that's why it's difficult to unravel the net impact in time and space. We saw from the previous slide that CO2 represents one of the major climate forcings, in fact, the largest component of the overall climate forcing that's occurring. But what's actually happening with CO2 levels? Well, that's very clear. The graph on the left there shows the trend based on data taken at Hawaii, which is very clean air, reasonably close to the equator, uncontaminated by local pollution sources. So it's really a measure of what's happening at the global level of CO2, and it's pretty clear that it's rising quite rapidly. Going back to 1960, running at about 320 parts per million, just recently passed 400 parts per million. So that's a pretty massive increase. That's a 25% increase in CO2 concentration in the atmosphere in just 50 years. And the trend is actually accelerating. And yes, you can notice that there is some variability in the net growth per year, if you look at the bottom right graph, because CO2 is not only being increasing concentration in the atmosphere, but it's also being absorbed by plants and dissolved in the oceans. So whilst we're pumping in CO2 out every time we burn fossil fuels, a significant proportion is in fact being reabsorbed by the Earth's systems. You can also see that there's a small annual fluctuation as the concentration rises and falls with the seasons as a function of temperature, but that's relatively small in the global context. The overall trend is very clear. As mentioned, some of the CO2 is in fact being absorbed into the ocean, and this is what's causing the changes in acidity in the world's oceans, and that has implications for corals, mollusks, etc., other forms of life in the oceans. And you can see the data taken there showing trends in surface ocean CO2 and also the pH levels. And again, very, very clear evidence of the changes in the world's climate system. So it's pretty clear that the average temperatures are increasing, that global warming is happening. It's also pretty clear that CO2 is one of the major factors, the major factor in fact, underlying that. But where does the CO2 come from? Well, CO2 is released every time, for example, wood burns. And that's caused by things like forest fires, which in turn can be caused by lightning strikes, etc. Animals also produce CO2 from conversion of oxygen, whereas plants, of course, do the reverse. They absorb CO2 and produce oxygen. So the Earth's atmosphere is in balance, with CO2 being absorbed both into the oceans and into plants, and being produced by animals and volcanoes and forest fires and a whole range of other natural causes. So CO2 levels have fluctuated over millions of years, which we'll discuss. But the issue is that CO2 levels are changing very rapidly due to man's burning of fossil fuels. We talked before about the rise in CO2 levels as measured in Hawaii from 320 parts per million up to about 400 parts per million over the last 50 years. The graph above shows CO2 emissions by fuel from burning fossil fuels, coal, oil and gas. And the key point here is that coal has been the driving force for most of that period in global emissions, but in particular in the last decade or so. And that's due to the rapid increase in coal consumption, particularly in China and to some extent in India, for power generation and for the steel and cement industries. Oil has been, however, if you go back 40 years, was an equal source to coal, in fact slightly larger source than coal in terms of CO2 emissions. And you can also see from that graph the rapid rise in CO2 emissions from burning gas, notwithstanding the fact that gas produces less CO2 per unit of final energy than coal. So the trends are very clear and very much upwards and relate to that level of concentration of CO2 in the atmosphere. So why do we burn all those fossil fuels? Well, about 40% goes into electricity and heat, about a bit over 20% to transport, another 20% for industry, 8% for residential, and 10% for others. So the combined share of electricity and heat generation and transport represents nearly 2/3 of global emissions of CO2 in 2010. If we look at the question of who's producing it and look at the trends over the last 20 years, then it's interesting we can see that the gigatons of CO2, that's a gigaton is 1,000 million tonnes, produced by the parties that signed up to Kyoto has actually been falling and slightly below the Kyoto targets. Whereas, unfortunately, there's been a very substantial increase over the last 20 years in CO2 emissions from what are called non-Annex 1 parties, principally China and some of the other developing countries. So that's been the big political debate in the last 15, 20 years about who's responsible for this increasing production of CO2, as well as, of course, who's been responsible for the historical production of CO2 from the days of the Industrial Revolution onwards. If we look at CO2 emissions on a per capita basis between different countries, then the picture is actually quite interesting. The red line at the top of this graph is the USA, and historically, until very recently, the US has had the highest level of CO2 emissions per capita of any country. However, unfortunately, we can see that the country in dark blue there, with the rising trend, and has recently taken over as essentially as the world's top producer of CO2 per capita, is in fact none other than Australia. We've now passed Canada, we've now passed the United States. If we look at the brown line, or the orange line I should say, near the bottom, starting near the bottom in 1971 and rising very rapidly, particularly from 2000 onwards, that's China, and you can see it's heading towards or just past 5 tonnes of CO2 per person per year. Compare that, for example, to Australia at about 17 tonnes per person per year. So China, on a per capita basis, still well behind the developed world, despite the fact that it's been rising rapidly. But as we shall see on a total basis, China has become the largest emitter. The final graph for this lecture shows that the total emissions of CO2 in millions of tonnes by country or by region of the world. And as mentioned, you can see the USA there down the bottom, very substantial contributor. The purple is the OECD Europe, and then above that you can see the rise in China, which is the orange band, and then also the rise in the rest of the world, which includes countries like Russia and Brazil and South Africa, etc., etc. Overall trends running from just under 6 billion tonnes to heading over 12 billion tonnes in that period between 1971 and 2010. So more than doubling the CO2 emissions over that period. So that concludes this series of this lecture, and we will look at other aspects in the following lectures.